Hi everyone and welcome to Activity 21. Today we are going to talk about the beginning of simplifying our trig expressions. Now before we can start talking about simplifying, we need to talk about some of the identities. And the first identity we are going to talk about is the Pythagorean identity. And this comes in the fact that when we have the unit circle, we can use Pythagorean theorem, so c squared equals a squared plus b squared, and we know that our c value is 1, a and b are sine and cosine, so cosine squared plus sine squared has to equal 1 squared, which is just 1. So our most basic trig identity is that sine squared plus cosine squared theta equals 1, and we can always rearrange these. For instance, if we subtract the cosine from both sides, we could say sine squared theta equals 1 minus cosine squared. Or if we go back to the original and subtract over this, the sine squared instead, we could say cosine squared equals 1 minus sine squared. And we'll see later today how sometimes these different identities and substitutions can be useful to us. Now, officially, we can take our original Pythagorean identity, which we sometimes just call the Pythagorean identity, the original one, and we can derive some other Pythagorean identities. For instance, if we divide everything by a sine squared, and simplify, what we end up getting is that when we divide this way, we end up getting with sine squared divided by sine squared is 1, cosine squared divided by sine squared is cotangent squared, and 1 divided by sine squared is cosecant squared. So our second Pythagorean identity, you could say, is this formula here where 1 plus cotangent squared equals cosecant squared. And similar to the others, we can rearrange these. For instance, if we subtract over the cotangent squared, we could say cosecant squared minus cotangent squared equals 1. Or if we subtract over the 1, we could say cotangent squared equals cosecant squared minus 1. And again, if we take this original Pythagorean identity, we can also divide everything instead of by sine squared. We can divide everything by a cosine squared and also get another set of formulas that we could potentially use. So for instance, when we do this, sine squared divided by cosine squared is tangent squared. And then we have cosine squared divided by cosine squared, that's 1. 1 divided by cosine squared is secant squared. So this is a third variation, and again, each of these, again, can be manipulated. So for instance, if we subtract over the 1, we could say tangent squared equals secant squared minus 1. Or if we subtracted over the tangent squared, we could say secant squared minus tangent squared equals 1. So again, these are some different formulas that we can use and manipulations to help us eventually simplify and solve things down. So for instance, we see some examples down below where this could be helpful to us. For instance, in number 1, if we know that sine squared plus cosine squared is our Pythagorean identity of 1, we can make that substitution in. And then up above here, we know that 1 minus cosine squared can be sine squared. And so instead of having all of that written, what we can have instead is just 1 divided by sine squared, which we know using a reciprocal identity could be cosecant squared. Or in the next example, 1 minus sine squared from up above is cosine squared. So then we would have cosine squared over cosine. One of the cosines in the top can cancel with the cosine in the bottom, and this would just simplify to be 1 cosine x. And then from up above, we have cosecant squared minus cotangent squared. We know that equals 1. And then we also have that secant squared minus tangent squared equals 1. And then 1 divided by 1 could just be simplified to be 1. Now, some review as well, we kind of talked about this on the last page a little bit. We also have our reciprocal identities, and we've been talking about these since even last semester, but we can rewrite each of our trigs as 1 divided by their reciprocal function. So sometimes that's useful to us. For instance, in the first one, 1 over secant squared could be rewritten as cosine squared, or 1 over cosecant squared is sine squared. 1 over cotangent squared is tangent squared. Tangent we could write a couple different ways, either as 1 over cotangent, or reminder, this could also be rewritten as sine over cosine, kind of depending. Same thing with cotangent, it's either 1 over tangent or cosine over sine. And then last but not least, sine squared over cosine squared can be rewritten as a tangent squared if needed. Now, as we finish up with a couple more examples of simplifying, especially using a lot of these together, sometimes we will want to use some of these helpful steps or hints. So for instance, we want to see if we can rewrite any of our trig functions in terms of sine and cosine, or using Pythagorean identities, or possibly their reciprocals to help us with simplifying. When we are multiplying, we want to see if things will cancel out. Remember, it's only going to cancel if it is located on both the numerator and the denominator in our fractions. Remember, everything is officially divisible by 1, so you can make all terms into fractions as necessary. Just divide it by 1 if needed. If there is division, keep the top of the fraction the same and multiply by the reciprocal of the bottom to sometimes be able to make that into all in the same fraction. We know if there are parentheses, sometimes it's helpful to distribute from the outside. And if there are multiple terms in the numerator and the denominator in common, you may need to factor out the common terms, aka think about greatest common factors is a tip as well. Okay, so these are just some helpful tips to kind of look over in case you get stuck on simplifying these. So we have a couple examples here. This first one, we have cotangent of x times sine of x times tangent of x. We want to see what this simplifies to be. So cotan can be rewritten as cosine over sine. Sine is also already itself, so we're just going to leave that in the top of the fraction. It's officially over 1. Tangent can be rewritten as sine over cosine. And what we notice is since we're multiplying, some things can cancel out. For instance, we have a cosine and a cosine that can cancel. We have a sine and a sine that can cancel. And all we're left with is sine of x over 1, aka just sine of x, is what this can simplify to be. In our next example, if we distribute through this sine of x, we would have sine times cosecant, and then minus sine times sine. And we can rewrite this sine times cosecant as sine, and then cosecant can be rewritten as 1 over sine. And then sine times sine is sine squared. Well, what ends up happening is these sines end up canceling out in the first part. Sine over sine is just 1. And then 1 minus sine squared x. If we check back to our Pythagorean identities, we know 1 minus sine squared can be rewritten as our cosine squared. So our final answer on this one, cosine squared x. Number 3 is interesting because there's a couple different ways you can go about it. You may notice on this one that secant squared minus 1 is equal to tangent squared x. So we would have tangent squared x, which is sine squared over cosine squared. And then we had 1 over secant squared, which might be more useful to us to write as cosine squared, but in the numerator, right? We can make that into cosine squared if we write it in the numerator. And now we notice we have a cosine squared on the top and the bottom that can cancel since we're multiplying. And our final answer is just sine squared x. Now, this is a good example of how there also, though, sometimes can be alternate ways to do this. So for instance, if we look at this example, and maybe you didn't see this Pythagorean identity, maybe you said, hey, I have a secant squared on the top, I have a secant squared in the bottom. And maybe what I could do instead, since this is, division by the same denominator, I can break this up into two pieces. Secant squared x minus 1, both of them, are divisible by that common denominator. So instead of having a least common denominator, it's like we're breaking it up into two separate ones. So what we notice on this, secant squared divided by secant squared, is just 1. 1 over secant squared can be rewritten as cosine squared. And then 1 minus cosine squared is our sine squared. So notice we got the same answer either way. There just sometimes is more than one way to view these problems. For our next example, it's another one where it might be helpful. We see some parentheses. Let's try distributing. So we have cosine of x, sine of x, times cotangent of x. And then we're also going to distribute that to the second part, right? And we have cosine of x, sine of x, times tan of x. Now, if we rewrite each of these, we have cosine x, sine of x, tangent is cosine over sine. And then same thing in part 2, we have cosine x times sine of x, tangent is sine over cosine. So in this first part, we have a sine that can cancel with each other. So now we just have cosine times cosine, which is cosine squared. In the second part, we have a cosine and a cosine that can cancel. So we are just left with sine squared. And then sine squared plus cosine squared is the Pythagorean identity. We know that equals 1. All right, last example here, number 5. Notice on this one, it's kind of interesting. We actually have both of these have in common a cotangent. Okay, so we have a GCF, a greatest common factor of a cotangent for both of these that we can factor out. So if I divide out a cotangent from the first part, I'm going to be left with, inside my parentheses, a secant squared. And notice in the second part, if I divide out a cotangent, cotangent divided by cotangent isn't 0, it's 1. And we know secant squared minus 1 is a Pythagorean identity. So I have cotangent of x, and then secant squared minus 1 can be rewritten as tangent squared. And then I have cotangent, which can be rewritten as 1 over tangent times tangent squared. So these can cancel, the bottom with 1 on the top, and we are just left with tan of x. Now I know this are a lot of different examples. We will definitely be working with more examples in practice in class. Thanks for watching.